Okay, we are going to review both loads and stability margins. So here we have the definition for how we calculate the gain in dBs and the angle when we are given a transfer function. So we are gonna do, to review this, we are just gonna do cases. So we are gonna do the first case, that is when we have a constant. So when our g of s is just k, and we're gonna see what is the both load of this. Okay. So the gain in dBs is gonna be equals to 20 log and the value of k and the magnitude of k. So that's what we are gonna get here. We're gonna get here 20 log k, and this is gonna be constant through the whole frequency range. Okay, so we don't have omega. Yeah, we don't have here an s, so we can change it for j omega. So it's just gonna be a constant 20 log k. And in terms of the angle, if you think about it in terms of, if we have here the plane and this is the real and imaginary, you can see that when we have just a constant, we don't have imaginary parts, so the angle is just gonna be 0 in for the vector k. And also when k is negative, when k goes this way, we can see that the angle is minus 180 degrees. So this also shows that when we multiply by we have a transfer function and we multiply by -1, we flip the result. So we are gonna have 0 degrees when k is bigger than 0, and we are gonna have minus 180 degrees when k is below than 0. Okay, now we are gonna see another case. Case 2, 0 at the origin. So this means that we have basically in our transfer function, g of s is gonna be equals to x, or x over something. Okay, that is a 0 at the origin. So here we're gonna have again our graph. Now for this, we are gonna see what's gonna happen when we have 0.1, we have 1, we have 10, 100, and okay, let's do it like this. Yes, like this. Okay, give me a second. Okay, at 1, at 10, 100, and 1,000. Okay, so let's first see the case when we have 0.1. So when we have 0.1, s becomes, well, always the magnitude is 20 log base 10, right? Log in, we are changing s for j omega, so here we are gonna have omega. So when omega is really small, like 0.1, the result of this is minus 20. So here we are gonna have minus 20. So when omega is really small, we get minus 20 at 0.1. Now what happens when omega is 1? So 20 log 1 is equals to 0. So let me draw it better. Let's say that here we have our 0. Okay, so this is 0. So over here we are going to have our minus 20, and over here we're going to have our plus 20. So we know that is going to be 0, 0.1 is going to be 20, and for 1 is minus 20, and for 1 is going to be 20. So this is going to go, and for 1 is going to be 0, sorry. So here is minus 20 and 0. Okay, that makes sense. So we are going to have something like this. And what's going to happen at 10? We're going to have 20 again. So at 10, you're going to have 20. If you see, this is just going to keep going like this with a slope of 20 dB. Now, how about the angle? Well, the angle is just going to be j, because here we have that the function is x. It's just x, and x we change for omega j. So if we draw the imaginary again, like we did with the constant, this time only we have the unit j here. So it is all 90 degrees. So we are gonna have here 90 degrees, constant through the whole frequency range, because it never changes. Okay, now we are gonna see the next case, case 3. When we have a pole at the origin. What it means? It means that we have 1 over x, so we are going to have 1 over omega j. So we can see here. Again, let's say that this is our 0 here, around here. Around here we have 0. Okay? So we do the same experiment, and we said we know that the magnitude is 20 log 1 over omega. So when omega is 0.1, or omega is really small, so we have here 0.1, we have here 1, 10, 100. So this is going to become 1 over 0.1, that is 20. 20 log 1 over 0.1 is 20. When log is 1, omega is 1, then we're going to still have 0, because it's 1 over 1. And we have 10, and when we have 10, this is going to become 1 over 10, and it's going to be minus 20. So if you see, it's just the inverse of the last case. So we are going to start here at minus 20, we are going to go to 0 at 1, and okay, we're going to start at minus 20, and this is plus 20. We're going to start at 20, 0, and then we're going to go to minus 20. That is the correct way. Okay, and this is just gonna keep going, and now we have a slope of minus 20. Okay, now in case of the angle, this time the angle is gonna be 1 over j, and we know that this is minus j, so it's gonna be the same. If we look our real and imaginary plane, we know that it's gonna be down here minus j, so it's gonna be minus 90 degrees, and that's what we're gonna put over here. It's minus 90 degrees from the whole frequency range. Okay, now we're gonna see the case 4, when we have a simple 0. A simple 0 means 1 plus s over some value, omega naught, or z. It depends of how you look in the books. And now we are gonna see this. Again, the magnitude is going to be 20 log. We are going to have omega over omega naught. So this time we are going to think what happens when omega is a lot smaller than omega naught. So when this one is a lot smaller, this whole thing will become really, really small, like almost zero. So when we have 20 log of 0, 20, this is gonna become, yes, I'm forgetting to put here the plus 1. So when this becomes 0, we are just gonna have log of 1, that is gonna be 0. Now, when we have the other case, that omega is a lot bigger, then this is just gonna be omega. So this is just gonna behave like omega. This one is not gonna matter. So if we look at this here, we said that until omega, we are gonna have 0. And then after we reach the part of omega, our it is just gonna increase with an slope of 20 dB, like it used to before when we have our zero at the origin. Now in terms of the angle, we have to think what happens when this is really, really small. For example, when omega naught is a lot smaller than omega. So let's say that we have 0.1 omega naught. So we know that we are gonna have 1 plus omega j over omega naught. So here, okay, so when our omega is like 0.1 of omega naught, then we know that our phase is 0. Okay, now our angle is 0 because this is gonna go to 0, this is gonna go to 0, and we are gonna have the angle of just the real part. In the other case, when these two are equal, when it finally reaches the value of omega naught here, so when we have omega equals to omega naught here, we are gonna have in our real and imaginary plane here 1 and 1. So this vector is gonna be like this, and here we are gonna have an angle of 45 degrees because these two are the same. So we are gonna have here 45 degrees. This is gonna grow up to 45, and then again when this one is a lot bigger than this, then all that is gonna matter is this omega, and so we are all just gonna have j, and j is gonna be 90 degrees just like before. So this is just gonna keep growing until we have okay, let me make it better. Here we are gonna have 45 degrees, and here when omega naught is a lot bigger than omega, when omega is a lot bigger than omega naught, and here we are gonna have 90 degrees, and it's just gonna stay like that as omega keeps growing. Now let's see the last case, and I hope by this time it starts making sense when we have a simple pole. So it's just like the other case, but this time we have 1 over s over omega. So this is just gonna turn our 1 over 1 plus omega j omega naught. Okay, and we're gonna do the same analysis. First, what happens in our magnitude when omega is a lot smaller than omega naught. So if this one is a lot smaller, this is gonna go to 0. When this goes to 0, this is gonna just be 1 over 1, and the magnitude of 20 log of 1 is just gonna be 0. So again, until omega naught, until omega is equals to omega naught, we're just gonna have 0 gain. Now, when omega is a lot bigger than omega naught, so when this one is a lot bigger, all that's gonna matter is omega, and we're gonna have 1 over omega. So this is gonna be a negative value of minus 20. So minus 20, we know that is gonna be decreasing with a slope of minus 20 dVs per decade. So when we have here 10 omega naught, it's just gonna keep going down like this. This is just like this case, but inverse because it's 1 over that. Okay, and in terms of on the angle, in this case, when omega is a lot smaller than omega naught, and we see here when we have one, well, yeah, when we do this, it's gonna be the same. This is gonna be 0, so we are just gonna have real part. So until omega naught, until omega is really a really small part of omega naught, we are just gonna have 0 degrees. And again, when these two are equals, we are gonna have 1, so it's gonna be 1/2. Here we're gonna have like 1 plus 1j. And again, when we have 1j, we get a negative angle, and this is again a 45 degrees angle. So until omega is equals to omega naught, we are just gonna have 45 degrees. Just gonna make it here so it fits. We're gonna have 45 degrees. When omega is a lot bigger, then all that is gonna matter is omega. So we are gonna have minus 90 degrees when omega is a lot bigger than omega naught, and it's just gonna stay like that. So those are the 5 most common cases, and from that you just combine them to make bigger examples. Now we are going to talk about both plot grain crossover, frequency, and gain management. Okay, so this is the initiation. So basically what this is saying that a system is unstable if poles are in the right, in the half right plane. So if we have any poles in the half right plane, our system is gonna be unstable. So we have to think in, and this is in our closed loop. So what we have to think, so what makes or what values in an open loop make the closed loop unstable. So if we have an open loop like this, what values are gonna make our closed loop? So if we have a transfer function of this, is the transfer function. The transfer function is gonna be x over y equals to g of x 1 plus g of x. So we know that this part over here can be 0. If it is ever 0, then this is gonna be unstable. So if g of x is equals to minus 1, then the system is unstable. So here in an open loop, if our open loop is ever minus 1, then we have a unstable system in our closed loop. So we have to make our open loop stay away from minus 1. And we can see the Bode plot of minus 1. So this is gonna be the Bode plot of minus 1. So for the gain, we are gonna have 20 log of 1. And we know that this, for all the examples that we have done, that this is 0 dB. So this is gonna be 0 in terms of gain. But in terms of the angle, this is minus 1. And when we just saw before, this is gonna be a minus 180 degrees angle. So we need to make sure that our graph or that our g of s stays away from this value. So for example, let's say that we have a g of s that looks something like this. This is just a random transfer function that I'm just trying to write here. So let's say that we have something like this. This is the gain Bode plot, and we have here the phase. So let's say that it looks something like this. So here at this point is where we have the frequency value that makes the system unstable. So we need to make sure that our graph, that when we may add a gain, we never make it go, that our cross here never makes it to this point. Because if we make a function, if we add a gain, when we add again, this is gonna go up. So that's the value of gain that is gonna make a cross through the frequency that make this open loop minus 1, and that's what we don't want. So this value of the difference here, this value is our gain margin. And similarly, here, down here, we're gonna have the value that goes from, we don't want our graph to cross this minus 100 degrees. So this value over here that goes from to a graph to this is gonna be our phase margin. So if we add a delay that decreases until here, we are gonna get a an unstable system. So those are the margins that we have to be careful. And the margin is, so the margin is how apart from this point g of x is. Okay, so let's do an exercise. Here we have our open loop function. They are giving us different frequencies to calculate the value of k, and they are asking us to, at these frequencies, what will be the value of k that makes this system unstable in a closed loop. So basically what they are asking us is, what values of x of k makes our system equals to -1, equals to 1. Okay, so let's see how we calculate k for each frequency. So we have that for 2000 hertz, s is gonna be omega j, so it's gonna be j to pi times the frequency, that is gonna be 2000. So this is gonna be 4000 pi. That is our value of x. So here we're gonna say 1 equals to k, the k that we want. We are gonna have in our first one, we're gonna have x, that is j, and this is j, forgot to put it here. So j 4000 pi over 100 pi, multiplying 1 plus for j 4000 pi over 1000 pi, multiplying 1 plus j 4000 pi over 5000 pi. Okay, and now we need the magnitude. That's why I put it like this. We can solve for k, and we're gonna need the magnitude of this. So there are many different way of doing it. You can calculate each individual magnitude, but I'm gonna do it separately. So we are gonna have here 40 for this part, 40j, 1 plus j4 times 1 plus j4 over 5. And this magnitude, so first we multiply all of this together. So we are gonna get minus 192 minus j88. And now with this we can calculate the magnitude finally, and that's gonna be 202. So this is the value of k that make our transfer function 1, and that's what we will get we are gonna get a unstable system. And for the angle, we are gonna need to take this part right here, because it's all of this but simplified, and we are gonna need to subtract each one of the angles. So well, we just saw in the void ploys, when we have a j4, a j, the phase is gonna be 90 minus, here we have uh, tangent to the -1, on the top goes the imaginary part, so inverse tangent of 4 over 1, the imaginary part over the real part, minus inverse tangent of 4 over 5 over 1. And when we calculate all of this, we're gonna get an angle of minus 24.62. Okay, so these are the this is the angle and the frequency that make the cross that make us cross the minus 180 or the word plot of -1. And now it's asking us to do it in MATLAB. So here I already have the script. So first, I'm just clearing everything. So we start with something new. I'm creating a variable in the system that I'm calling k variable. This is because they're asking us for two examples, one for 2000 and one for 750. And just did all the manual calculations with one just to show it, but the next one we can just do by using MATLAB. So 750, 2000 is gonna be our first k. And here I'm just creating a state variable so it is easier to write the transfer function later. So first we find k at 2000, so we know that the s is gonna be j 2000 times 2 pi. And then we just plug it that k is equals to the absolute value, I mean the magnitude of our transfer function. And then we define the open loop transfer function. So let me just make sure. Sometimes MATLAB, when you don't put the denominator in brackets, have finicky behaviors. So okay. So we have here our k, that is gonna be this one, the one that we just calculated, and then we just put the Bode plot. We just plot the Bode plot, and now we run it. It's taking a while. Okay, now here we have our Bode plot, and if we right click and showing characteristics and show minimum stability margins, it's gonna show us all the stability margins. And here we can see that we have our angle of minus 24.6, and around here we are also gonna get our frequency of, we have 4000 pi, that's around 12.5 kilo radians per second. No, yes, yes, it's basically what we have around here. It's just that it's really hard to put it right in the 0 dBs because it is pretty small. But yeah, we know that around here we're getting our 4000 pi in our frequency, and we are crossing at that frequency that made us go below. So if we also here in MATLAB, you can just click show all the stability points, and when you click on them, it's gonna tell you that it's not stable. And we could do the same for our other example of 750. And here again, show minimum stability. So 750 in hertz times 2 pi is gonna be 4712. So let's see if maybe we can see something like this. Okay, I was wondering why we were getting the same result, but here I just hard coded the 2000, so that's why. Okay, now we can run it. And let's try to see if this time we get the crossover. Yes, 4000 and something. I just can't click right at 0 dBs. But that's our frequency. And here we can see the angle that we will get. Okay, And now here we haven't crossed it yet, the 180, but just at this point. Okay, I hope this helps.